farther apart than solids and liquids and can move independently. Without a container, gases can spread freely. Though we cannot always see gases, they surround us.
Four fundamental gas laws discover the relationship of pressure, temperature, volume, and amount of gas. Gas laws have been around to assist scientists in finding volume, amount of gas, pressure, and temperature when coming to matters of gas.
Gas law consists of four primary laws. These laws are Charles' law, Boyle's law, Gay-Lussac law, and combined gas law. However, we're only going to focus on Gay-Lussac law.
Gay-Lussac law states that the pressure of a given mass of gas varies directly with the absolute temperature of a gas when the volume is kept constant.
This means that when the temperature of a sample of gas in a rigid container increased, the pressure of gas increased as well. The increase of kinetic energy results in the molecules of gas striking the walls of the container with more force, resulting in a greater pressure.
French chemist Gay-Lussac discovered the relationship between pressure of a gas and its absolute temperature. Gay-Lussac's law is very similar to Charles' law, with the only difference being the type of container. Whereas Gay-Lussac's experiment uses a rigid container, while Charles' law experiment uses a flexible container. Gay-Lussac's law can be expressed using a mathematical expression. V sub 1 over V sub 1 plus V sub over V sub 2 or V sub I over V sub I plus V sub f over V sub f. Whereas V sub I is initial pressure, Ti initial temperature, V sub f final pressure, and V sub f final temperature.
Let's have an example. The gas in an aerosol can is under a pressure of 3 atm or atmosphere at a temperature of 25 degrees Celsius. It is dangerous to dispose of an aerosol can by incineration. What would the pressure of the aerosol can be at a temperature of 845 degrees Celsius? So our given in this problem is our initial pressure is 3 atm or atmosphere. Our initial temperature is 25 degrees Celsius. Our final temperature is 845 degrees Celsius. What is asked in the problem? The final pressure is asked in the problem. So before we're going to solve for the final pressure of the aerosol can, we must convert the initial temperature and final temperature to Kelvin. So 25 degrees Celsius converted to Kelvin, we should add 273.50. It results to 298.50 Kelvin, while the final temperature, 845 degrees Celsius, at 273.50 is equal to 1180.50 Kelvin. So after we convert the unit to Kelvin, we must solve for the final pressure. So our formula is initial pressure over initial temperature is equal to final pressure over final temperature substitution. So our initial pressure is 3 atm substitution, and then our initial temperature is 298.50. Next, since we don't have the final, since we don't have the given for the final pressure, we must look at this. Next, we must substitute the final temperature, which is 1180.50 Kelvin. After we substitute the given to the equation, we must cross multiply. So 298.58 must multiply into V sub or final pressure. And then we must cross multiply or multiply 3 atm to 1180.50 Kelvin, as you can see. And then we must divide both sides by 298.50 Kelvin. Why? In order for us to eliminate 298.50 Kelvin at the top and leave V sub. So in order to solve this, we must
kami ngayon sa
Chem Lab, sa Chemistry Lab. Bakit tayo pupunta ng Chemistry Lab? Ano bang meron?
Gagawa tayo ng experiment! Yay!
Yes! Gagawa tayo ng experiment.
So, andito na! Papasok na!
Yes! Say hi guys, our section mentoring. Please, say hi to our vlog.
Say hi to our vlog!
Nag-charade sila guys. Nag-charade sila.
So guys, nandito na kami.
Nandito na kami sa Chem Lab. Ipakita yung pinipisa sa taas. Sa Chem Lab. Gawa tayo ng experiment. Hey guys! Welcome to the Chemistry Laboratory. And today we will conduct an experiment to demonstrate how Gay-Lussac's law works.
The materials we will need are drinking glass,
Plastic Tupperware or small plate or any container to hold water,
Candle, matches, and water.
But before we're going to conduct the experiment, we must have safety precautions. We should wear lab gown, tie our hair, and have adult supervision. So the procedure for this experiment is to fill the plastic container or plastic Tupperware with water and then put the candle in the plastic container and light it by using matches or match. Be careful when handling with fire. After that, we must put drinking glass inside or on the candle. Let's have this experiment a little closer. Gay-Lussac's law states that when a fixed amount or mass of an ideal gas is kept at a constant volume and in a closed system, then its temperature and pressure are directly proportional. What this means is that when a gas's temperature increases, its pressure increases, or as its temperature decreases, its pressure decreases.
In our experiment, our drinking glass is filled with gaseous air molecules. The energy from our flames transfers to the air molecules, exciting them by raising their temperature. When the air molecules in our beak are excited, they try and spread further apart, but because our beaker won't expand like a balloon, the volume of space our air molecules can take up is limited.
As they try and expand in volume, the air molecules press harder and harder against the walls of our drinking glass and the water at its base. This increase in air pressure under our glass causes the water level under it to be pushed lower than the water level outside of it. The higher the temperature or the more energy the air molecules get, the more pressure will be created.
As the candle flames burn, they use some of the oxygen contained in the glass for combustion. The products of this reaction are carbon dioxide, gas, and water vapor. As more and more hot carbon dioxide gases and water vapor are produced, they fill up the top of our glass, forcing the oxygen in our glass that the candles need to burn lower and lower until the candles are extinguished.
Once the flame is extinguished, the air molecules under our glass begin to cool off, dropping in temperature and losing their excitement. This causes the amount of pressure our air molecules are exerting on the sides of our glass, and the water at its base to drop as the pressure drops. The air under our glass wants to be equal to the pressure outside of our drinking glass.
This need for balance causes a pull on the sides of the drinking glass and water at its base because it's much easier to pull water into our drinking glass than it is to collapse the sides of our glass.
The water in our shallow container is pulled into our glass, raising the water level under the glass, equalizing its pressure by changing the temperature. Under our glass, we can clearly see the directly proportional relationship between the temperature and pressure of an ideal gas. This relationship is known as Gay-Lussac's law.
That's all for today's video. For more upcoming videos, subscribe to our channel and don't forget to ring the bell button. Bye guys! It's great!